All right, an introduction to definite integrals. This is something that we've kind of already talked about. We've expressed that this really just means the area underneath this curve. This one is timesing it by some constant k, but let me get a look at this expression. Maybe it's just the area underneath the curve between a to b. That's all this really means. Well, now we're going to show that the antiderivative is actually equivalent to the integral, and that it's the area. It is the area underneath the curve. So, a couple of things, right? They're trying to just remind you here that if you have some constant, you could just simply pull the constant out of the integral and integrate. We've already done that before when we've done the antiderivative. And if you're adding functions together, you could separate them. We've talked about that as well. Let's go to the next. We have some other properties here. Again, these are all things I think that we have discussed, but now we can officially see the rules for them. If you're asking the area between two or the same point, right, then that means you have a width of 0, which gives you an area of 0, regardless of the height. If f is integral on a to b, that means that a is less than b. You have to put the a in front. If you don't put the a in front, if you put the a on top, then that automatically means that this is the opposite amount of area, right? It's a negative amount of area. And this could very well give you a negative area, but then it would be a negative times a negative, so then it would become positive, right? So that's possible as well. And then you can also separate out different parts of the area underneath the curve. So look at this picture here below for this next one. So it says on 3 closed intervals. So imagine it goes from a to b is the whole interval, a to c is this first part, and c to b is the second part. All they're saying here is that if you add up this area and you add up this area, it should equal the whole area. And that makes sense, right? That these two areas combine to make the whole thing. And this really is what kind of the fundamental theorem of calculus is based on. We'll talk more about that later, but that's really this basic idea that these areas can add up. And we'll play with this more in class, but that's the basic notion. You could separate this out as two integrals, obviously, and calculate them separately, and then that would give you the whole area. All right, let's go to the next page. All right, so now we have some problems to work through. And we've worked through these problems, or these types of problems, before. But the way we've done them before is we've graphed it out. I've said, hey, look, this is just, if you think about this, it's just a line at 2, and it's from 4 to 10. So if you're kind of think about this as a graph, here's 2, and here's 4, and here's 10. And so here's this line, and so the area underneath this curve is just this rectangle that is 6 by 2. And so this thing is going to equal 12. That's how we've done in the past. And that's fine. There's nothing wrong with that. That's absolutely true. But here they're just asking us to evaluate the antiderivative, because in the next video we're going to find out that these two things are equivalent. So all they really want us to do is to find out that what is the antiderivative of this? So let me just kind of show you how you would do that. We've already done the antiderivative, right? This is going to be 2x. And we could write 2x plus c. And then what we would do is we would just put a little notation, a little like slanted line here that goes from 4 to 10. Okay, so that's what this equals. It equals 2x plus some constant. And we're evaluating this thing from x is 4 to x is 10. That's what this really means. Well, we're going to play with this notation a little bit more in the next video. And the goal is to show that this is going to end up equaling exactly this. And so we'll get there. We'll get there. But for now, let's just practice taking the antiderivative. Couple of things that you could see right here. This looks like a complicated antiderivative, but it just wants you to find the definite integral. So we could see that it goes from 5 to 5. So we should just stop right there. We don't even have to look at anything here. This is just going, it has no width. If you think about that, the area has no width, so we can just tell this thing has to be 0. And so you should be able to do the next one pretty quickly as well. Yeah, you should see that goes from 2 to 2. That has no 0 as well. Now we could still calculate the antiderivative here. This would be 17x squared over 2 minus 2x. And we could say this is going from 5 to 5. But it doesn't really matter because we already know this whole thing just equals 0, right? And in the same way here, we could calculate this thing. we could say this is x cubed over 3 minus 2x squared over 2. And I guess you can throw the plus c in here, although when it is a definite integration, again, we're going to find out we don't need to do that. But this is going from 2 to 2, so there is absolutely no width here, and so it equals 0. Okay, so this one just says fix the upper and lower limits. See, we could tell right away 15 is obviously larger than 5, so this should not be written like such. So we're going to just fix that. We're going to put it in the right order. But remember, when we put it in the right order, that means we need to change the sign. So this is really like saying negative, and then this would be 9x minus 2 dx. Now, you could distribute that negative through. That's fine. You can make this a negative 9x and a positive 2, or you could just leave it out there because think of this as like a negative 1. It's a constant, so it's out in front. It doesn't ask us to evaluate it. All it asks us to do is fix the upper and lower limits, so we're done here. All right, example 4. Use the properties of definite integrals to rewrite the integrals. Okay, all we're going to do is rewrite it. So the first thing I see is that these are two separate things subtracted by a minus sign, and so we can separate these out. And if I am just separating out this front part, this 17 is just a coefficient, so technically I can write it like this. 17 times the integral from 0 to 5 of x squared dx. I could almost kind of imagine me distributing this dx each term. Minus, now there's a 2 out in front, right? There's a 2, so I could just say minus 2 the integral from 0 to 5 of x dx. And again, they didn't ask me to evaluate, they just asked me to rewrite, so that's all I'm doing here, is just rewriting this. Okay, let's. Why don't you try part B here on your own to rewrite that one. So you could rewrite that as 2 integrals and take out those constants. Give it a shot, pause the video, and then check back when you're ready. Okay, so we could separate out as 3, the integral from 2 to 4 of x squared dx, plus 2 times the integral from 2 to 4 of x dx. Again, we're not evaluating. All we're doing is rewriting. Okay, that's a pretty simple video. I'll see you guys on the next one.